Hey everyone, this is Mr. Adler. This lesson's about circular motion. Circular motion can be difficult to understand because there are a couple of things happening at the same time, a couple of different motions, and they happen quickly, so the result is tough to follow. But don't worry, I think we can see these actions more clearly to help us understand what's going on. There are many examples of circular motion, from the orbits of moons and planets to the spinning of tires. You can see our Rio Olympian at the bottom getting ready to do the hammer throw. Hope the Olympics go well. So it's an action that occurs all around us, and we can take advantage of it if we understand it. So let's take a look at basic circular motion. I've got a large washer on a string. Can you see the two motions that are occurring simultaneously? It's kind of difficult to do that because the object is moving all around. I think it will be helpful if we slow the action down, maybe even pause it once in a while. Let's take a look at it again. Let's do it in slow motion. Yes, my cat is fascinated with science. First action I want you to notice is how I begin getting the washer to move in a circle. I actually just start by throwing the washer. Perhaps only for an instant, but I hope you can see that the washer begins by traveling in a straight line. This is due to Newton's first law. Actually, all of circular motion is Newton's first law, just two motions at the same time. But let's focus on one at a time. If that throw in the beginning was the only motion, the object, the washer, would go in a straight line. That's Newton's first law. An object in motion will stay in motion in a straight line unless acted on by an unbalanced force. It's a silly example that I have right here, but let me just show you the first motion of the two motions that give circular motion if there wasn't a second one around. I'm going to start by throwing the washer, but I'm not going to hold on to the string. It's kind of silly. Okay? But if you notice, the string, the washer, went in a straight line. Something like that. That's what happens. An object in motion will stay in motion in a straight line unless acted on by an unbalanced force. So what I'm trying to get you to see is the object isn't moving in a straight line. There must be an unbalanced force. For this example, we're going to ignore gravity, pulling our object towards the ground, because I'm trying to show you an example that can happen anywhere, like out in space. Hopefully you can see that right in the beginning. But it doesn't last. Very quickly, the direction of the object changes. So watch for the straight line, right in the beginning in slow motion. There's the straight line, and then it starts turning. That's the other part of Newton's first law at work. There must be an unbalanced force affecting the motion of the object because it doesn't stay moving in a straight line. Where's it coming from? If you look, you should see that the motion begins going in a circle the moment the string attached to the object gets taut. Watch this. Right there. I'm holding on to the string and keeping the object from flying in a straight line. That's because I'm pulling on the string. That's the unbalanced force. I'm pulling. That's a force. It's unbalanced because there isn't a pull away from me. Here's where the tough part of circular motion happens. If I wasn't holding on to the string, the object wouldn't fly directly away from me. To prove that, let's look at the circular motion again. But this time I'm going to let go of the string. It starts in a straight line, then it starts to turn. Okay? So right now there are two motions going on. But now I'm going to let go of the string. I'm going to let go of the force pulling in. Here we go. Now, it's flying in a straight line when I let go, but the direction of that straight line is a little something that confuses people. Okay? I let go right here. If I'm not pulling towards it anymore, a lot of people think the washer's going to fly straight away from me since I'm not pulling towards it. But that's not what happens. What really happens is the washer goes this way. And if we're looking at the circle, that's tangent to the circle. I know those aren't the best arrows in drawings, and we're going to clean that up in a second. And there it goes. Okay? Not perfect for my drawings, but pretty decent. Okay? We can clean this up by getting rid of this video. You should see that the object didn't fly straight away from me, but it turns out to be tangent to the circle. At any moment, if I'm not holding on to that string, the object would continue, as Newton's first law states, in a straight line. And that straight line is always perpendicular to the circle, wherever the object is at that moment. So you have tangential velocity of the object occurring at the same time that the string is pulling the object towards the center. Let's say we've got an object going in circular motion like that. That pull towards the center is called centripetal force. The definition of centripetal force is center-seeking force. That force keeps the object from traveling in a straight line. It changes the object's direction. This is the part of circular motion that's so hard to see because it's happening so fast. I'm constantly holding on to the string. So I'm constantly pulling on it. So there's constant centripetal force being applied. That's the symbol for it, centripetal force. Therefore, I'm continuously changing the direction of motion. Even though the object's speed might be staying the same, it's constantly changing direction. That's a change in velocity, and a change in velocity is known as acceleration. There's constant acceleration towards the center of the circle. Okay? Here's another reason why things get strange. Looks like there's two arrows there. This force causes the acceleration. If we draw it like that, it can be very confusing. But really, it's the acceleration vector that represents the changing motion. So we couple that with the tangential velocity. Okay? That's a lot of words. Here it is in picture form. We've got this object that wants to go in a straight line. Right there, it wants to go that way. The centripetal force is pulling it towards the center. That's what centripetal means. That results in centripetal acceleration. Those are the two motions happening at the same time. Maybe you studied vectors, maybe you haven't yet, but we can resolve vectors by doing something like this. Tip-to-tail method. Both those motions happening at the same time give us this result. And the object starts going that way. Now, when the object gets over there, again, continuously, it wants to travel tangentially to the circle, and there's a centripetal acceleration towards the center. Those taken together result in this motion. Now these little vector diagrams that I'm drawing them kind of big so that you can see. That's why they overlap, undercut the circle. These are happening every instant of time that the object's trying to move around this circle. So there's these little triangles that I'm drawing are actually very small. But I'm hoping that you can see the basic idea of these two motions. The tangential velocity and the centripetal acceleration, giving you a result. An instant later, the tangential velocity and the centripetal acceleration, constantly changing direction of this object, constantly moving it in a circle. This is happening every instant of time, giving us what we see. All right, let's make it a little bit easier. I think the math might be a little bit nicer to take a look at. So hopefully we can cool down with this. Typically, we are given the velocity of our object and the radius of a circle. We can calculate the centripetal acceleration using the formula centripetal acceleration is v squared over r, where v is the velocity in meters per second, and r is the radius of our circle in meters. Let's do an example. If a water skier was at the end of a 10-meter long rope and was whipping around the boat with a velocity of 9 meters per second, what would be their centripetal acceleration? Here's our formula. And don't forget, even though 9 meters per second isn't changing as a number, this whole idea is you're on a water ski, you're a water skier moving around on that rope. So even though you're doing 9 meters per second, you're constantly changing direction. For you to change direction, that means your velocity is changing. You're accelerating. There must have been a force applied to you to cause that acceleration. And we can calculate this acceleration. We know that the velocity is 9 meters per second. We're going to square that in the formula. Divided by the radius of our circle is the length of the rope, because you're moving around at the end of that rope. Okay? That rope's attached to the boat. That's the arc you're swinging around in a circle. We simplify this a little bit. 81 over 10. That gives us 8.1 meters per second squared. That's not too bad, I hope. Now, could make it a little bit tougher. You could also be given the centripetal acceleration and have to calculate something else. If an object moving in a circle with a velocity of 8 meters per second experiences a centripetal acceleration of 16 meters per second, what must be the radius of the circle it's traveling? The numbers aren't too crazy, but I do get worried sometimes because what we're looking for, in this case, is an unknown in the denominator. Sometimes that freaks people out. If you have listened to me ever, you know that. Do a slightly small but extra step. Cross multiply first. Get that R, get the X out of the denominator. Oops, I messed up. Don't forget to square the 8. That's a 64. R equals 4 meters. Some people, when they look at that R, forget that that's R in the denominator. So make sure you do the extra step of cross multiplying, getting that R out of the denominator. There are some other ways this topic can be more difficult. There can be some extra geometry that you might need to do to calculate the velocity. Some 2 pi r kind of stuff. If the circular motion's in the vertical direction near the Earth, gravity will affect the motion depending on whether you're going up or down the circle. Make sure you have a good handle on the lesson you've seen today, so you will be ready to move into new applications. You can always review this video again and pause it at the tough spots so you can absorb all the good information. And don't forget to ask your teacher for any questions before they take you to another level. I hope this helped.